Hello everyone, welcome to the new episode of the group theory course. In this episode, I want to talk about the dihedral groups and the Quaternion group. In the last episode, I talked about the generators in a group and the cyclic groups. We know that the cyclic groups are very special groups that are generated by just a single element. But for other groups, there are a lot of groups which are not just generated by one element. They can be generated by a lot of elements. And in this episode, I want to talk about those two examples of groups which are generated by more than one element. The first one is the dihedral group. The dihedral group is defined like this. We denote the dihedral group by 2n for some integer n, and it is a group generated by two elements r and s, and those elements have a property that the nth power of r equals to square of s equals to the identity, and also r times s equals to s times r inverse. This is the definition of the dihedral group 2n. And here the n means n is an integer. So for different n, the dihedral group is different. But the dihedral group is actually related to the polygons. So for the dihedral group 2n, it is related to the n-gon polygon. And the relationship is like this. Like the elements of the dihedral groups are the actions or operations on the n-gon shape. And the r means the rotation of the n-gon shape, and the s means the reflection of the n-gon shape. We can look at an example. So, like for example, if n equals to maybe 4, okay, then we are talking about d8 because it equals to d2 times 4. And so it should relate, this group d8 should be related to the operations or actions on the 4-gon shape, which is a square. So we have a square, and we can denote the vertices of this square by a, b, c, and d. And then the the r element in the dihedral group d8 means we rotate the square maybe in the clockwise direction, and the s here in the dihedral group means we flip this square along this line. Okay, this is r, this is s. Okay, we can check if those two elements related to those two operations satisfies those two properties of the dihedral groups or not. So first we check the s squared equals to 1. That means if we apply s to this square by one time, we get because we do reflection, so a vertices will go to the place where the b was, and the b will go to a, and also d will go to c, c will go to d, because we are reflecting along this line. So the result is like this: it's b here, a here, and D here, and C here. And then we reflect or flip this shape again. What we get? So A will go to B, B go to A, C go to D go to C, C go to D. Then what we get is A becomes here, B is here, C go to here, D is here, and we can see this is the same as the original square. So that it means that we apply the S operation on this square by twice, one time, two times, like this. It is equals to S square applies to this square shape, and that is equal to the original square, which is equivalent to say that we just apply the identity operation to this square, because identity, if you apply identity on like any other elements, it does not change anything. So the idea is you apply identity operation here, it does not change the square. So this shows that S squared equals to 1. Similarly, for the rotation R, we can do the same thing. So A, B, C, D. If the rotation is clockwise rotation, so we apply it once, we get so here A will go to B, B go to C, C go to D, D go to A. So A becomes here, B go to here, C go to here, and D is here. And then we apply it this operation again, R. We get here A now go to B here, so A is here. B goes to C here, so B is here. C go to D here, so C is here. D go to A, so D is here. Okay, then again we apply the rotation. So this time we will have, with the similar idea, A will be here, B will be here, C here, D here. Okay, and the final step, we do the rotation again. Then A will goes to here, B will goes to here, C is here, D is here, and then we can see this is equal to the original square here. So we conclude that R to the fourth order equals to 1. So this satisfies the property here, because this n is equal to 4. Okay, how about this property, the second property? So we apply the the S at first, which is the symmetry at first. Then we rotate the shape. It is equal to, we do the inverse of rotation, which is rotate the shape in a opposite direction, and then apply the the flipping. So here, so if we do RS, which means we do CD. Okay, so this means that we want to apply this operation, operation of two operations. So we apply the S first, which is S. It becomes to because we flip this shape along this line, so we get a B here, A here, D here, and a C here. Then we apply the rotation R, we get rotation, we rotate in clockwise direction, so A becomes here, and D goes to here, so D is here, C goes to here, and B is here. So this is what we get after we apply RS. And how about this is RS, how about SR inverse? So that is, we apply the inverse of R first, because R is rotate clockwise, so the inverse R should be the rotation of counterclockwise. So what we get is like this. We by rotating it in counterclockwise direction, then A will go to C. So A is here, and this this is D. So A is here, D goes to C. So this is D, and the C will be here, and the D will be B will be here, and then we apply S. Then we get when S is along, like flipping along this line. So after applying S, we get C goes to here, so this is C, B goes to here, this is B, and this is D, and this is A. So we can say those two results are the same. So that means like we apply the RS to the square is equal to we apply SR inverse to the square. So if we just ignore the square, we get RS equals to SR inverse, which is what we want here. So this means this dihedral group 2n when n equals 4, the elements of this group are just the operations, the rotation operation and the flipping operation for the square, which is a four-gun polygon. So this is also true for any n, for n is integer. Okay, this is a dihedral group, and another group is Quaternion group. Okay, Quaternion group is a group look like this. We usually write it as a Q8, and it is generated by also like two elements, ij, and in this group, I times j is defined to be another element k, and then I square equals j square equals k square equals to 1, not 1, equals to -1. And this is the definition of the Quaternion group. So we can say that here we should note that this -1 is the inverse of 1. So so like if we have like I square equals to -1, then I to 4 is equal to like a -1 square, which is 1. So the elements I, j, and k all have order 4 in this group, and this group is called the Quaternion group because it is related to the Quaternion elements and Quaternion numbers, and the Quaternion numbers are a generalization or extension of the complex number, and it is very useful to represent the rotation and the movement in the for the points in the 3D and three-dimensional space. So this is another example of a group generated by two more than one element. Okay, that is the a place where we should stop in this episode. Thank you for watching. See you next time. Bye.